Hello, everyone. Welcome to my presentation. I hope everybody is doing well in these uncertain times. My name is Sakib Haque, and I am one of the authors of our paper, Improved Automatic Summarization of Subroutines via Attention to File Context. Now, I understand that the name of our paper is a mouthful, but the idea behind it is actually relatively simple. But before we dive deep into the paper and discuss these ideas, let's talk about the problem of source code summarization in general. Now, what is source code summarization? Well, it can be defined as the task of generating natural language description for source code. Source code summarization is a rapidly expanding research area in the software engineering domain, especially with the explosion of AI technology and deep learning models. Now, you may wonder, why do we need software documentation? Well, one of the reasons is to help a programmer understand what a subroutine does without having the need to read the entire source code themselves. These documentations are often the backbone of documentation tools such as JavaDoc or Doxygen. Now, I'm about to show you a Java function with its corresponding JavaDoc comment. You don't need to read the source code, but notice how the JavaDoc comment structure allows the programmer to write more information about the subroutine. Notice here that the programmer can write information about the parameters and the return value and include a short description of what this block of code does. This can be helpful, not only to navigate the code, because now someone coming back to the code months later doesn't have to read these 10 to 12 lines of code, but they can just read that one short sentence summary to understand what this block of code does. Furthermore, it can help someone navigate through the related methods of the project without getting bogged into the details of the code. Traditionally, source code comments are written by the programmer. The problem with this approach is that programmers do not want to write these comments. Engineers think that this is just a waste of time. They think that they will just remember what the code does when they come back to it later. Additionally, since this is a manual process, it's also very time-consuming and hence expensive. The academic response to this problem has been nagging for years to encourage software developers to embrace an automatic source code comment generation tool. And there has been a flurry of recent research that is working on making this happen. Early efforts were based on heuristic approaches with manual encoding of human knowledge, such as sentence templates. But just like any other problem in modern computer science, heuristic approaches have been superseded by data-driven approaches by using neural networks. Nearly all these recent AI-based solutions to the source code summarization problem are inspired by NMT technology, or neural machine translation technology, from NLP, or natural language processing research area. Any typical NMT problem and neural model is fed a pair of sentences, one in a foreign language and a corresponding translated sentence in a native language. For example, Ami cha khete chai is a Bengali sentence, and it would be fed in as the input to get the hopefully predicted output of I want to drink tea in English. When directly applied to source code, this means that models are fed code and their corresponding summaries, with the code serving as one language and the English description serving as the corresponding translation in the native language. Quite a few different iterations of this approach have been tried, with promising but limited success. I quickly want to discuss some of these methods before I talk about how our model fits in the landscape of source code summarization literature. The first work I want to discuss is by Ear et al. This model uses plain encoder-decoder architecture from NMT and applies it for code summarization. This was a foundational work, especially impressive given its straightforward application of off-the-shelf NMT technology. Later, Hu et al. Proposed an improvement to this technique by using the AST of the function. They believed that the AST should give more details about the code behavior than just words of the code, thus resulting in better and improved summary prediction. Since the tree structure of the AST was not compatible with the sequential input of the encoder-decoder model, they designed a structure-based traversal, or SBT, which is essentially an algorithm for flattening the AST into a sequence and using the components of the AST to annotate words from code. LeClair et al. Later showed that while incorporating the information encoded in the AST is good, it shouldn't be blended together with the words of the code in the same input sequence, since the AST and words from code contain two very different types of information in two very different structures. And related work in image captioning has shown that better results are achieved when different input types are processed separately. To facilitate this idea, they treat the AST sequence in a separate recurrent net with separate attention mechanism and concatenates the results into a context vector at the very end, just prior to prediction. At around the same time, Alon et al. And Alamanis et al. Noted that it is not optimal to flatten the AST into a sequence, since this forces the model to learn tree structure information from a sequence. To solve this problem, Alon et al. Extracts a series of paths in the AST and treats each path as a different sequence. Alamanis et al., on the other hand, propose using a graph-based neural network to model the source code and learn the representation of code. They applied it to the code generation task in their implementation rather than a code summarization task. Even more recently, LeClair et al. Uses graph neural networks together with source code sequence as separate inputs to a model. They use a graph neural network-based encoder of Alamanis et al.'s graph-to-sequence model to model the AST of each subroutine, and combine it with the RNN-based encoder to model the subroutine of a sequence. We have also seen work done by Shido et al. In similar vein, where they add an extension to the generalized LSTM for the tree structured data called tree LSTM. Regular tree LSTM cannot handle a tree that contains nodes having an arbitrary number of children and their orders simultaneously. ASTs, however, generally have such nodes, and the multi-way tree LSTM model addresses this issue by using LSTMs to encode the information of ordered children. These methods I just described are just a few noteworthy models among many others in the field of source code summarization, and they are all based on a key assumption that is made in almost all NMT applications. All information needed for the translation is contained in the sentence. In this case of source code summarization problem, the input is the source code, be it the AST representation, be it the text of the code. All these models assume that everything we need in predicting meaningful summaries of program subroutines is available in the input of the source code of that subroutine. In the next slide, I'm about to show you a piece of code. Take your time to look at the code, read it, and try to guess what the summary comment of that code would be. Pause the video if necessary, and take 30 seconds to think, what summary comment would you write for this program subroutine? Now, the reference comment for this function is sets the intermediate value for this flight. Well, since I can't actually see anybody's reaction, I'm going to assume that most of you were like me, such that you assumed that it is a setter and that the method sets the intermediate value. But the question remains, sets the intermediate value of what? There is no information in the function that could possibly help us identify that it is setting the intermediate value for a flight. Nothing about the function even remotely hints at anything related to flight. So unlike traditional NMT tasks, source code can often not have all the information needed to produce the English summary comments. This is important because here we see that a key assumption of NMT technology breaks down. Once again, we have just realized that source code can often not have all the information needed to produce the English summary comments. So what more information do we need? What else should we fit into the model in addition to source code and its AST? Well, this is where our key novelty comes in. We take a look at other functions in the file. We look at the other function in the file to provide us with the context information. On your screen now is the first 12 functions in the file that also contain the method we just discussed above. As you can notice, the word flight appears for the first time in the third function of this file. To build our model, we use an incremental approach. This diagram shows a simple RNN encoder-decoder architecture of neural source code summarization model. This is a faithful implementation of Ear et al.'s off-the-shelf NMT model using unidirectional GRUs. As you can see, this architecture is very simple. It models the code using word embedding space and a recurrent neural network. The code text labeled here is simply the sequence of tokens from the source code for the function. We can then see how the attention is calculated for the encoder input to the decoder input, for every position in the decoder to every position in the encoder. To create an output prediction, we concatenate the attention-adjusted matrix of the encoder input and the decoder input, and use a fully connected network to learn how to combine these features from each input. This part of the model now outputs the predictions for the next word in the summary. Next, we add the AST information. We add the AST in 3 different ways based on literature: by flattening the AST to a sequence, by using paths of the AST as separate sequences, and by using graph neural networks. As you can see in area 6, we have another attention that is computed, this time between the AST input and the decoder output. Finally, we add the file context information, the key novelty of our approach. The input itself is a code text for every other function in the same file. The format of this input is an n by m matrix, where n is the number of functions and m is the number of tokens in each function. We model the input by using a trainable word embedding space. Notice that we share the same embedding space as the code text. Next, we use one RNN per function in the file context. That is, we only use the final state of the RNN. We build a 2-dimensional matrix in which every column is a vector representing a function in the file context. Of course, this vector is the final state of the RNN for that function. Thus, when computing the attention, we rewire the attention mechanism to calculate the attention, this time between each position of the summary, to every function in the file. Let's now take a look at our experimental findings. For our paper, we had 5 baselines: transformer model, which is an attention-only NMT model; the ATTEN-GRU, which is a faithful implementation of Ear et al.; AST ATTEN-GRU, which is the implementation of LeClair et al.; graph-to-seq. Now, this is a graph neural network-based text generation system by Xu et al., who uses nodes and edges of AST as input. This is basically inspired by Alumnus et al.'s work on representing ASTs using graph neural network. And finally, we have code-to-seq, which is our faithful implementation of Alon et al. Notice here that for all of these baselines, we first implement the model without any file context information, and then we add file context in a new version of the model. And in all cases with file context added to the input, we see an increase in the BLEU score. This is important because here we want to note that we do not view our approach as being in competition with any of these other models, but rather an improvement to all existing models. We do not make any particular recommendation for a model. All we are saying is no matter what your model is, whenever you add file context information like we did, you see an improvement in your BLEU score and thus an improvement in the quality of the summary predictions. Here we have a graphical representation of our results. The y-axis is the BLEU score, and notice how the y-axis starts at 17. The blue shaded area in each bar is the BLEU score that you get for the base models. The yellow shaded region is the improvement that we get on top of every base model after we add the file context information. Let's look at the example that we have been discussing so far. This is the function that we had, and here is the activation heat map of the attention matrix in the AST ATTEN-GRU model with file context added to it. Notice that for this example, the ATTEN-GRU baseline model predicted sets the intermediate value for this unknown token. AST ATTEN-GRU model also predicted the exact same information. This is because, as we had noted before, this function does not actually give any information for us to be able to predict the intermediate value of what. However, when we look at the file context information, we did get the proper output, sets the intermediate value for this flight. When we take a look at this activation map, we see that the activation is highest while predicting the word flight, while looking at function 3 of the file. If we look at the first 12 functions of the file, we see that function 3 is the first time that the model sees the word flight. I have a second example here that I would have liked to go through, but it looks like I'm running out of time. So I'm going to skip over this. But if you want to learn more about this example too, or if you want to learn more about all the other stuff that we discuss, here is a link to our paper. Our paper is up on archive, and you can download it and read through it to learn more about it. Here's a link to the code that we have for our project. If you want to download the code and then implement our work on your machine, you can do that. And here is a link to my website, my personal website, where you can learn more about me and the group that I work with. Well, I would once again like to say thank you for listening to this talk, and I hope that I'll be able to see everyone in person once this pandemic is over. Thank you.